Today's lecture is on Lagrangian Mechanics, and so the last three lectures we've been looking at harmonic oscillator systems, and immediately prior to that we did a really short, quick lecture on Lagrangian Mechanics just as an introduction to the concept. And in the next block of 3 or 4 lectures, I want to deal with Lagrangian Mechanics a lot more rigorously than I did back in lecture 3. And you'll remember back there we had this idea, we had a thing that we called the action that was accumulated along some path, and what we wanted to do was choose the path that minimized the action because that's the correct path between 2 points that an object will take, okay? And the way we handled it back there was to chop that problem into individual little pieces and just consider the motion of one of the pieces of the path and use that as a sort of discretized problem to get us the idea of an Euler-Lagrange equation, okay? Doing that as a discretized problem, it's a correct way to get the method to get it out, but it's not quite so elegant as doing it properly via a calculus-based route. And so today I want to spend some time doing the calculus-based route for this so that you've seen it done in a sort of mathematically proper approach. And so that brings us to a topic that we call calculus of variations. And calculus of variations is basically the idea of trying to find the minimum or maximum of a quantity that's expressed as an integral. Okay, so we talked in lecture 3 about functionals. What we're doing here is dealing with those sorts of systems from a calculus perspective. So when we do this, I'm going to pull action out today and not bring action back until the next lecture. I really want to just deal with paths because it's a lot simpler in terms of the calculus to just think in terms of path lengths. And that naturally brings us back to a problem that we dealt with in lecture 3 and we called the lazy walker problem. Okay, so you have this idea here of you want to get from point A to point B and somehow you have to choose a path. And there's multiple ways to get there. Sometimes there's a not sensible way to get there that might take more time or more energy or more effort. And there's a smart way to get there that, you know, takes less energy or less time. And when you ask which is the path that a person would take, they will take one path and not the other. So similar idea to what we had in Lagrangian Mechanics, just stripped back to path lengths, okay? So to do the mathematics on this, we need to build a little bit of a problem together. And so what we need to do is treat a path between 2 points, 1 and 2, in an arbitrary way so that we can then solve out what the shortest path is, okay? So what we have here is y-axis, x-axis. We have some point 1 at x1 and y1, okay? And we have some point 2 here, x2 and y2. And we can choose some path between 1 and 2, and here, just for sake of argument, we've drawn some windy path. And as you know, this y is going to be a function of x, and it's going to be a function of x because for every point along this x-axis, there's a point on the y-axis that corresponds to that path, right? So if I'm going from point 1 to point 2, at every particular point x along that path, I'm going to have some position y. And so the path becomes this y as a function of x. And then what we do is work out the length of an element of this path, add all the element lengths together to get the full length, and then we try to minimize that length, okay? Some of you will spot already that this is kind of a trivial problem. Everyone knows this from more or less when they're a young child, that the shortest distance between point 1 and point 2 here is going to be a straight line, right? It's why we walk in straight lines between 2 points where we want to go from and go to. But what's nice here is we can actually mathematically prove that that actually is the case. We can look at arbitrary paths and ask which is the shortest path between those 2 points. And that's something we're going to set out to do here. It's going to seem like a trivial problem at first, but later on what we'll do is we'll apply it to some other places where you really don't know what the shortest path is, but you want that shortest path. And then in the next lecture, we'll build action back in and we'll start to head quite strongly towards Lagrangian mechanics, okay? All right, so where this mathematical derivation starts is we're going to consider a length of an element of our path here, ds, right? And this would just come from Pythagoras rule. It's basically a little change in dx, a little change in dy. You add those together and that gets you your ds, okay? So what you have is ds is equal to square root dx squared plus dy squared. Then we have one other thing that we know in here. We know that dy is equal to dy on dx dx. And there's two ways you can think about this statement, right? One is that all we've done is said that dy is equal to dy, obviously, and we can multiply that by 1, and that 1 can be dx on dx. So what we can write here is basically dy is equal to dy on dx times dx, knowing that the two dx's will cancel out and you get something that's equal. That's one way to see it. The other way to see this is you can imagine a little element dx, right? And it will come up and the two edges of it will hit this curve, and then you can go across, and so you can map dy relative to dx by knowing what the slope is when you come up and intercept and go across, right? And that slope is dy on dx. So really what we're saying is we're taking a small element dx and projecting it across into the dy axis using the slope of the line at that particular point. Okay, so there's two ways we can see this. All right. We need to treat y as being a function of x. So let's get a little explicit about this for a second. If we want to take the derivative of y, so we want to write a thing y dash, and let's be clear, it's going to be a function of x as well, then it's going to be d on dx of y of x, right? Which we can basically write as dy on dx, okay? So we can now take our term just up here and we can recast it very slightly so that it looks like this. Y dash of x dx. Okay? Alright. The reason why we've done this is that we want to take our term for ds up at the top and rewrite that term ds at the top. Okay, so ds is now going to be square root of dx squared plus y dash of x squared dx squared. Okay. With that in place, we can divide through by dx because it's common term, and then take the square root and pop it to the outside. Okay, so what this thing is going to be is 1 plus y dash of x dx. And the last step here is basically to get the length of the path. The length of the path is going to be the integral from 1 to 2 of ds, which is just going to be the integral from 1 to 2 of square root 1 plus y dash of x squared dx. Okay? I'm going to stop this result here. I'm going to hold it. Let's call it 1. I'm going to stop this part of the problem here. We'll come back to it a little bit later in the notes, because before I get to it, I need to set up something, and then I can come back and take this thing and use it a little bit further. Okay, so let's take a quick break in the problem at this point. What we want to do is now work out how to minimize L. And what we have to do is minimize something that's an integral already of some function, right? And so what we have here essentially is, in physics, something we call a variational problem. What you do is you take a path or something, some integral or whatever it is you're doing, and you vary it very slightly, and you're looking for optimizing or solving that problem of the variation, right? In this particular case, we're looking at trying to minimize something associated with that path by varying that path, okay? And what we're going to do here is do this by fully calculus-based route and show that we get essentially our Euler-Lagrange equation from lecture 3 back in much the same way. Okay, so the way we're going to cast this problem is a little bit more general than the lazy Walker problem that we just did. It has to be, because otherwise it won't adapt to a whole pile of problems. And then we'll come back and we'll solve that lazy Walker problem using the architecture we build here. Okay, so if we look at what we just had from the lazy Walker problem and consider what we're trying to solve here, what we're interested in is, we'll call it S for now. We're interested in going from some point S1 to some point S2. We have some function here, and it can be a function of y of x and y dash of x, and could be a function of x as well on its own, dx, where y dash is just dy on dx, just to be clear. Okay, I'm going to use dashes all the way through this problem, and so if you see an exponent that looks like a 12, it's actually a dash 2, okay? Just so you don't get confused later in the notes. So all we've done is just generalize the problem we just had, because if you think about your lazy Walker problem up here, what you're really doing is you've got some path, you're going between 2 points, 1 and 2, and you've got some function that accounts for that path that you want to minimize, okay? And we've just made it a general function here, knowing some specifications for it. And so we have 2 fixed points here. We've got S1, which is just x1, y1, and an S2, which is just x2, y2. And we know that y of x1 is going to be y1, and y of x2 is going to be y2. Okay, so that we're just mapping as you normally would with functions in this particular case. So let's take our idea of paths for a minute and consider it a little bit like this. We have 2 points in our graph, S1 and S2. And as you know, these run from x1 to x2 in this direction, and y1 to y2 in this direction, right? And so we could have a correct path in here, and call that y of x, right? And we can have what we call an incorrect path, or a wrong path, right? And so it might come up here and do some funny stuff and go across to that position, right? And we'll call this big Y of x, just so that we're connecting these two together, right? And this correct path in here, we will decide later on, minimizes S. Since we know from physical principles that that's what it's going to do, so we'll set this thing up so that when we solve this problem, we're minimizing whatever this integral we've built is at the front. Okay, so the way we can handle this is to take our wrong path and basically treat it as a variation on the right path, right? So what we can do is we can write this as the right path plus, and this is always my hardest Greek letter to write, eta of x, where eta of x is basically an addition to make the right path the wrong path, okay? Now the important thing here is we've got common endpoints. And in the way we do the mathematics here, it's actually very important that this has common endpoints, because if it doesn't, then a whole pile of little pieces along the way through the maths right out into lecture 9 and 10 breaks down and the problem's no longer tractable, okay? So really, really crucial point here. And it is that y of x1 is equal to y of x1, and y of x2 is going to be equal to y of x2. And the reason why this matters is that it means that this term eta at x1 is going to be 0, and this term eta at x2 is also going to be 0, but over the intervening path in between, this function eta is not 0. Okay, so we really just specify that eta must be a function such that at the two endpoints it's equal to 0. Right? Okay, so what we did above was just have a right path and one wrong path, and that's not really enough. What we want is a right path and a whole pile of wrong paths so that we can actually sift through the wrong paths to work out how to get closer to the right path. Okay, and so the way we do this is we introduce what we call a family of wrong paths. And you could kind of do this any way you want, but the really easy way to do it is like this. You go y of x is equal to y of x, so we're starting with the correct path. And what we're going to do is add alpha times eta of x to it, okay? And what this means here is if alpha equals 0, we have the correct path. And so you can imagine alpha can go, it can be 0.2, 0.4, 1, 2, -1, -2, so forth. And so what it would do is add this sort of incorrectness to the correct path. And then what we need to do is solve through, and we know that when alpha is equal to 0, that correct path, those incorrect paths don't contribute, and you're on the correct path for this, okay? So what we're aiming really to do here is to find of s as a function of alpha, aiming to find the minimum of s as a function of alpha. Okay, so what we need to do this is get s ds on the alpha, sorry, write alpha down there, equals 0 at alpha equals 0, okay? And so this is a fairly simple calculus problem we can do here. We're basically just aiming to minimize a function on the basis of something that sort of tweaks the path a little bit. Okay, so let's work through this and see where it heads for us. So we can now take our integral above and just recast it slightly. Okay, so this thing is now going to be s as a function of alpha from x1 to x2 of f big Y dash x dx. Okay, and so now what we're basically doing is allowing our family of wrong paths in here and searching through for our ideal case. We can write this here as x1, x2, big F, y plus alpha eta, y dash plus alpha eta dash x dx. Okay, and we know that because up here we've basically got y is equal to, big Y is equal to little y plus alpha eta. Okay, and so that's all we've really done in there. We now want, what we're really interested in here is ds alpha on d alpha. And so here we take d on d alpha, integral x1, x2 of f of dx. Okay, I won't write the functional dependence in here just to keep it tight. And of course we can pull this derivative inside. So what this really is integral from x1 to x2 of df on d alpha dx on the end here. Okay, let's we've already used equation 1, so let's call this equation 2 just to keep track of things. Okay, so to get to the next step here, we basically need to use the chain rule, and I'm going to do it with all the steps in here just for a little bit of completeness. Okay. So the chain rule looks like this: d on dx of f of g of x is equal to f dash of g of x times g dash of x, okay? And we can now apply this rule to just df on dx. And I'm going to just make one little tweak just up here. This is actually a partial derivative, being formally correct. So this now is df on dy dy plus alpha eta on d alpha. And the reason why I haven't written df on dy plus alpha eta as the bottom down here is that my variables are in y and so forth, okay? So that comes out of there, plus df on dy dash dy dash plus alpha eta dash. That'll be d alpha as well, plus df on dx on d alpha. Okay. All right. We know here that if we take, let me go to red because it's clearer. If we take this integral here, sorry, this derivative here, it's basically eta. And if we take this one here, it's basically eta dash. And if we take this one here, it's basically 0, okay? So what we would get here is eta df on dy plus eta dash df on dy dash, okay? And those of you who have done real analysis courses will spot that that looks completely normal and so forth, okay? So if that logic doesn't make sense, you may want to just go back and do a little bit of review of chain rule from real analysis courses. Okay, so what we can do is we can now take this thing here and put it into 2. So what we have is ds of alpha on d alpha is equal to integral x1, x2 eta df on dy plus eta dash df on dy dash dx equals 0, okay? And that equals 0 on the end is basically because we're looking for a minimum, right? We're trying to find the case that minimizes this. And the thing that we have above is going to hold oops, 2 there. Under the scenario where the 2 endpoints end up being 0, right? If we break that, then things go a little bit wrong in here, okay? So we can consider this integral up here as essentially 2 terms in here. And what we're going to do is take the second term and we're going to do an integration by parts. And I'm going to spell this one out a little bit as well, simply because this trick comes up again and again in the next 4 lectures, right? We do this more than once. So you'll remember your expression for integral by parts. Some of you might have seen it in high school. If you haven't, you've definitely seen it in first year. U dv equals VU minus, sorry, it's only one for minus, minus integral V du, okay? And this term in here, VU, UV, it doesn't matter which way you put it around. I always got into the habit of putting it the other way around so that it matches the one on the end, and then basically going from by parts involves flipping the order and then dealing with both the certain part and the minus sign. Okay, it's more a trick for me to remember than a mathematical requirement. So our integration by parts here, we're going to take the second half, and you know that any integral of something that's a sum is the sum of the integrals, right? So we're really just stripping off the second half of this now. We've got integral from x1 to x2 of eta dash, and let's just for the moment make it clear it's a function of x. Df on dy, that'll be y dash, dx, okay? Now, if we use integration by parts here, what we're going to get is a definite term. So eta of x df on dy dash. Okay, so you can already see I'm starting to make clear which one I'm considering my u and which one I'm considering my dv, right? So let's just point this out explicitly. This one is my dv and that one is my u at the moment, okay? And so that's why you can see over here I've now got v, and then here I've still got u, right? And that's going to go from x1 to x2, and we're going to also have the integral here, x1 to x2 again, 2. Now we've got v du, okay, so this is going to be eta of x d on dx of df on dy dash dx. Let me pull it across just a tiny bit. One of the great skills in physics is actually working out how to get things in so that you don't run out of edge of page. And you can see after many, many years I'm still not perfect at it. All right, so we've got this thing. The really crucial point in here, and this is one that turns up again and again for the next few lectures, so I want you to notice this one carefully. This thing here is going to be 0. And it is going to be 0 because we know that eta at x1, let's do this in black, eta at x1 is equal to eta at x2 is equal to 0, right? So at the two ends of this component here, this term here is 0, which drives the whole thing to 0, okay? And this is another reason why we really require this endpoint 0 thing for eta, because if we don't do this when we try to do this integration by parts, we accumulate all these excess terms that become a real nightmare, okay? And so what we're really left with here is just this first part and the last part. And this first part and this last part is kind of nice because once you know these two endpoint relations are going to clean you up, and we can more or less assume this for the rest of Lagrangian mechanics, really integration by parts becomes something rather simple. It just becomes integral of u dv is equal to minus integral v du. And so what we can do at any point in our Lagrangian mechanics problems is basically just swap u and v for which one's d and which one's not d, as long as we carry a sign change, okay? And so we're going to use this trick again and again and again in here, and it entirely relies on the fact that we know that the endpoints are going to behave themselves, okay? All right, so we can now put this integration by parts back up into this term just here, okay? So let's do this. We've got ds of alpha on d alpha is equal to integral from x1 to x2 of eta, and I'll strip off the function part of this now. So df on dy. And often the trick here is just to specify what it's a function of enough and in the right places that someone knows what's going on. You don't need to write it all the time. And that's, again, one of the skills that comes from doing lots of problems. You start to work out where this is important, where it's not important. Okay, so this is now, we can do our little swap up here. So this is going to be now minus eta d on dx of df on dy dash. And we have our dx out here, and we're going to make this go to 0, okay? And of course, we've got a common term of eta in here, so what we can rewrite this as is x2, x1, eta of x. Let's put it back in just for a moment. Actually, let's not put it in. Doesn't matter too much just here. Df on dy minus dx, d on dx, df on dy dash, okay? Dx equals 0. Now, what we have here is we're trying to force ds on d alpha to go to 0, right? And we can see that there's two possible ways to do this. One is that we can make this 0, and the other is that we can make this 0. One is sensible, the other one is not, and the fact that the other one is not makes the first one the answer. So if we make eta of x go to 0, what we've basically done is just wiped out the problem, right? Because all we've said is that every incorrect path, big Y, has alpha times 0 all the way along that path, and so it collapses to the correct path, and all we've done is just basically make the whole problem vanish. Not the smartest option. The other way to do this is to take the term here on the right and make it equal to 0. And if you do that, then you can keep your eta non-zero except for the endpoints and still minimize ds on d alpha, okay? And so this ultimately is exactly what we do. We know to get ds of alpha on d alpha equal to 0 means we need to have df on dy minus d on dx, df on dy equal to 0, okay? And we kind of need to do this, and this is why I mentioned a little bit earlier, at or near alpha equals 0, because you can imagine that there might be positions where this function has a maximum or a minimum that are a long way from the correct path, and while technically they obey the mathematics here, they're not the correct path, okay? So this is why I specified a little bit earlier that this should be at or close to alpha equals 0, okay? It's very rare that we need to worry about that, but there can be problems where you do need to think about that one, okay? But ultimately what we need to do is basically pay attention to driving this thing to 0, and you'll recognize this. This is our Euler-Lagrange equation. Just hiding in a slightly different appearance than it did the other day, okay? You can imagine it's wearing a red t-shirt instead of a white t-shirt. It's the same fundamental thing, it just has slightly different terms stuck in it at the moment. I think this is a good point to take a break because we've actually got a really useful result, and in the next half what we'll do is we'll go back to the lazy walker problem. We'll look at proving that the shortest path is a straight line. It's very quick and easy to do. We'll look at some other shortest paths as well that are kind of interesting, and then finish off for today. So let's take a break.